All right, time to begin. Couple things. So double integrals. It looks like, as far as I can tell from what the class notes showed, it looks like all the double integrals that were covered in class or they talked about and on the homework are basically over regions that are either squares or rectangles. Right? Your limits of integration look like we're always constant. So for example, I saw something somewhat like this in class. Like, let's make it not too terrible. The integral from 0 to pi over 2, the integral from 0 to, sure, 3 of 2y cosine of x dy dx. And so what makes this example kind of less interesting, in my opinion, is that all of our limits of integration are constants, meaning your region of integration is a rectangle. We could draw it. It's really easy to draw. We just have y going from 0 to 3 and x going from 0 to pi over 2. So it kind of looks like this region here. That's our region R of integration. When the region is a rectangle, if you needed to, although you shouldn't ever need to really, you can always just interchange the order of integration without doing any sort of work really. This would totally be the same as the integral from 0 to 3 of the integral from 0 to pi over 2 of 2y times cosine of x times dx dy. So this is somewhat worthwhile to know, but maybe not super important. So just to note, if all the limits of integration are constants, then we can interchange the order of integration without any effort. Very easily. Literally just by switching which limits are first, which limits are second, which dx and dy comes first and second. The process of integration is still the same as it was before. So if we look at this left-hand version of this, well, we always work from the inside out. It's a great movie, by the way, if you haven't seen it. If you feel like crying, like, right. If you feel like crying and you want to see a good movie, Inside Out, excellent movie. Don't feel like crying, I don't recommend watching it. So anyway, working from the inside out, we're integrating first with respect to y. So this cosine of x is just a constant multiple as far as y is concerned. The antiderivative, I can say the antiderivative of y is y squared over 2, but I'm going to pull in the 2 there and say the antiderivative of 2y is just y squared. So we're going to get still the integral from 0 to pi over 2, and then the insides are going to be y squared times cosine of x, evaluated from 0 to 3, bless you, dx. And this is where I personally would probably have chosen to write y equals 0 and y equals 3 to remind myself that I'm only plugging those things in for y, not for y and for x. You might also notice that the dx here still says we have to integrate with respect to dx, so we shouldn't be plugging into the x's yet. So we're going to plug in for the y's. We're going to get the integral from 0 to pi over 2 of 3 squared times cosine of x minus 0 squared times cosine of x dx. Normally I wouldn't write that because I know it's supposed to be 0, but just to make sure that you know that if that wasn't a 0, like if that was a 1, you'd have 9 cosine x minus 1 cosine x, and then you could combine those together to get 8 cosine x. So we're integrating 9 times cosine of x. We're going to get negative 9, sorry, nope, positive 9 times sine of x. Apologies, I was taking the derivative there. So the antiderivative of 9 cosine x is 9 sine of x, evaluated from 0 to pi over 2. We plug in, we get 9 times sine of pi over 2 minus 9 times sine of 0, which is going to be 9 times 1 minus 0. Which is 9. Looks like the rectangle. Nothing more to do there. So there's not a well, actually that's not true. There's a little bit here. So double integrals, I think these are really boring personally because you don't get to have the fun part of where you have to change the order of integration. But if the yeah, I'll keep an eye on the homework and see like because all the homework problems were just like I mean the homework problems also were written like have you looked at the homework for this section yet? So if you look, I'll show you. Why not? Okay. So if we look over here at Canvas for just a moment. All right, 1 second. Okay, I already have this up. Maybe not. Nope, I sure didn't. Okay, Canvas. Look over it. I can show you Canvas. So we're looking at the 17C class real quickly here. You look at the pages. And the, oh yeah, and the week 5. And there's the double integrals homework. It's kind of wonkily written, in my opinion, but here are the problems, right? And so if you look at all these problems, I'll just point out this first integral, all the limits of integration are constants, all constants, all constants. And for the second one here, where we have the function given this way, and we have to integrate over the region where x is between two constants and y is between two constants, there's not a lot of work to be done as far as finding the region of integration. It's kind of already given to you. We might look at one like this last one here. And then this last question, or these last two questions here, still both constants, still both constants. So it doesn't feel like he's setting you up to even talk about any of these order of integration issues. So I don't want to clutter you or trouble you with that if it's not going to be coming up. But if it is, well, I'll keep an eye out. And here's the tendency, by the way. But let's do one more here because I would like to. Yeah, that's not really one here. Which one's that? Do this one here. Sure. I'm gonna make it slightly more interesting just 'cause I can't help myself. So we'll do this next problem and then we'll move on. Well, unless there's questions you have, but let's look at this example. So let's say we want to find. Yeah, sorry. Yeah, we'll do this one. So find the average value of the function f of x, y equal to e to the y squared over the region R, which is bounded by the curves x equal to 1/2 y, y equal to 6, and x equal to 0. Yes, it's not a rectangle because it's just too boring. Point of interest. So just like back in 17B, when you were finding average values, the average value in 17B, I'll just point out in 17B, the average value is just going to be like the integral from a to b of f of x dx divided by the length of the interval. Well, now that we've added an extra dimension, instead of being the area divided by the length to get the average height, it's going to be the volume divided by the area to get the average height. So in 2 dimensions, it's going to be essentially the double integral over your region of your function of 2 variables, d, whichever way you want it, divided by the area of your region. And you can either find the area of your region, well, you might have to find the area of your region by doing the double integral of 1, or you might just be like, hey, it's going to be a triangle, and I know how to find the area of a triangle. Because often our regions are nice geometric shapes if they're not just squares or rectangles. So cool, let's set it up. Actually, before we set it up, let's draw the region. So normally with these square rectangle ones, you won't have to do this really, but we're going to do it here one more time. So let's see. This is not too bad to draw. So there's x equal to 0. Here's y equal to 6. And x equal to 1/2 y or y equal to 2x looks vaguely like this. And I point out that if y is 6, x is going to be 1/2 times 6, so x is going to be 3. That's the point 3, comma 6. There's the point 0, comma 6. There's the point 0, 0. I just want to make sure everyone's super clear that we couldn't write this region of integration using just constants, right? If you said y went from 0 to 6 and x went from 0 to 3, you'd be describing the entire rectangle that included the bottom half down here. We are only looking at this region here. So if you're describing any region other than a rectangle or square, you're going to have some function that has a variable in it other than not just a constant. Again, so far he hasn't talked about that in class. So, and I'm doing a little bit extra here, but this problem's just so good I can help myself. All right, so let's go ahead and set up the average value. The average value is going to equal the double integral, and I'm going to wait to write my limits of integration here because I want you to see something. We're going to be integrating e to the y squared. Do we know how to integrate e to the y squared? That's a bad question. Is it possible to integrate e to the y squared? It is not. So that tells us something. We should not start off with y as the inner variable. Because if we try to integrate with respect to y, we're going to get nowhere. So we know if we're given something impossible like this, we should start off with x on the inside, y on the outside. Meaning my inner limits of integration should be the x bounds. So the x bounds are from left to right. They're a left boundary of x equal to 0 and a right boundary of x equal to 1/2 y. And then the y bounds are, well, this strip can go as low as y equals 0 and as high as y equals 6. All that's going to get divided by the area of our triangle, which I think we can calculate. Let's see. The height of that triangle is 6. The base of that triangle is 3. 1/2 6 times 3 is 9. Not too terrible. Questions before we keep going? Okay, let's do it. So this is going to be, we're going to integrate the inside. I don't see any x's there. So as far as I'm concerned, e to the y squared is a constant like 7. And the integral of 7 is 7x. So the integral of e to the y squared is going to be e to the y squared times x. We saw the outer limit here. The inside is going to be x times e to the y squared from x equals 0 to x equals 1/2 y. And we solve a dy. And instead of saying divided by 9, let's say multiply by 1/9. Give ourselves a little bit there. We plug in the limits of integration. We're going to get 1/9, the integral from 0 to 6 of 1/2 times y times e to the y squared y. And now I hope you all can see that we're going to have a nice u substitution. Right? The derivative of e to the y squared is e to the y squared times 2y. So I need a 2 there, or I don't really. Actually, I can just kind of make it happen. But right, we could, sure, I could multiply by another 1/2 and a 2 to make that part nice. I know I'm kind of doing my u substitution atypical way for me, but I think you all can see what's happening. So then the antiderivative of 2y e to the y squared is just going to be e to the y squared, because that is the derivative of e to the y squared. So then we're going to get 1/2 times 1/9 times 1/2, which is going to be 1/36. And the integral of 2y e to the y squared is e to the y squared evaluated from 0 to 6. So we're going to get 1/36 times e to the 36 minus e to the 0. And that's the average value or average height of this function. Yeah, over this region. Kind of neat. So again, what that means is if you kind of graph this surface over this triangular region and then try to like make it all be level so that you still have the same amount of volume under a horizontal plane, that would be the height of your horizontal plane, which is gigantic, right? E to the 36 is a super huge number, right? Like billions and trillions, like even beyond. But we don't really care that it's a big number or not. We just care about finding the thing. So there's an example of average value. It's taking your volume, dividing it by the area of the region. Not too terrible. And how are you guys doing? One that's less complicated. So I'll have you set one up. So set up the integral for the average value of what have I got here? Let's see. That's not what I'm looking for. That's one as well. F of x, y equal to 20 plus x, sure, x, y over the region where 0 is less than or equal to x is less than or equal to 10, and 20 is less than or equal to y is less than or equal to 40. Go ahead and set up the integral / equation for that average value. You don't have to draw the region, but you certainly could if you wanted to. All right, let's go ahead and take a look. So what's the area of our region? Yeah, it's 200, right? Because x is between 0 and 10, y is between 20 and 40. So essentially the base of my region is, or my region is a rectangle whose base is 10 and whose height is 20, and the area is 10 times 20, which is 200. So you could write this if you want to as 10 minus 0 times 40 minus 20, if that's a little more explicit about what's going on. And then for my volume, my double integral, you set it up in one of two ways. It can either be the double integral from y equals 20 to y equals 40, and then x equals 0 to x equals 10 of my function. And then it's going to be dx dy. Or if you prefer, you can set it up the opposite way. X goes from 0 to 10, y goes from 20 to 40, 20 plus xy dy dx all over 200. Either way is totally legit. And then let's go ahead and calculate, just to make sure that we're on the same page as far as doing it. So let's do it this first way. This is going to be equal to, I kind of like writing it as a fraction first, but then I feel like it takes up too much space. So then I usually just write it as 1 over whatever that number is times my integral. It's 1 over 200. The outer integral stays, so we're going to have the integral from 0 to 10, and a dx at the end. But then we're going to integrate the inside with respect to y. So the antiderivative of 20 is going to be 20y. And the antiderivative of x times y is going to be x times y squared over 2. Evaluated from 0 to 10. I also picked this one to do instead of that one because I knew the inside was going to have a 0, so it's going to have less pieces at some point. But either way, we're fine. Plugging in 10, we get 1 over 200 times the integral. Sorry, nope. I made a mistake. I did make a mistake, yeah. So hopefully you can see my mistake. My mistake is both methods of integration are from 0 to 10. So I integrated with respect to y, which means I was doing this one, not that one. Oops. So I need to change the limits of integration. Instead of from 0 to 10, they should be from 20 to 40, which is going to be more work at this stage, but less. So, all right, we'll plug in 40. 20 times 40 is 800. And 40 squared is 1600 divided by 2 is also 800. So we get plus 800x minus plugging in 20. 20 times 20 is 400. 20 squared is 400 divided by 2 is 200. So plus 200x. I would make the choice of simplifying this before I integrate it again. Like I don't want to integrate both these things. I might as well just combine them together. Same thing here. So let's rewrite this as 1 over 200 times the integral of 800 minus 400 is 400. And 800 plus 200 is, sorry, minus 200 is 600. And I was making sure I didn't make any silly mistakes. Okay. All right, so now we're gonna integrate. I suppose it would be not unwise. Well, it'd be not unwise to write my limits of integration 0 to 10, 0 to 10. It probably would make sense to factor out a 200 at this point from the inside here, right? It seems like a real easy thing to do. This can make this slightly easier. So we could write this as the integral from 0 to 10 of just 2 plus 3x. We want to make it just look a little bit gross. Less gross, right? You can think of either factoring out the 200 or multiplying the 1 over 200 through. 1 over 200 times 400 is just 2. 1 over 200 times 600 is just 3. So then we're going to integrate. We're going to get 2x plus 3x squared over 2 from 0 to 10. That's going to be 2 times 10 plus 3 times 100 over 2, which ends up being 20 plus 150, so 170. And that is the average value of this function over this region. So let me ask you all, are there other things about double integrals you would like to see or have me talk about? I feel like I've kind of exhausted it, but maybe there's something I'm really missing that I think is important. Okay. What I'll say then is before moving on to kind of the next section in the textbook, I remember I did talk about how we were going to do a absolute maximum / minimum problem over a triangular region. I kind of forgot to do that last class. So let's go back and do a problem like that just so I can keep my promise. And I do think it's worthwhile to see. So let's go back and do, unless there's questions or comments or concerns about this first. All right, so we'll go back a little bit and talk about this problem here. Yeah. Keep my notes in order sometimes. So here's the problem we want to do. And this is absolute max, absolute min. So find the absolute maximum and minimum of the function f of xy equal to 3 plus xy minus x minus 2y on the triangular region with vertices 0, 0, 0, 5, and 5, 0. And I usually like to draw the region first. I feel like it's helpful. Again, we're not, I feel like we could do two questions with it. We could also find the average value of this function over this region, but we probably won't. Let's draw the region. So I've got my vertices 0, 0, and 0, 5, and 5, 0. Most of the time with these absolute max min problems, if your region is triangular, it is almost always going to be the case that the non-vertical or horizontal part of the triangle is almost always going to be a line whose slope is either positive or -1. Like it doesn't have to be that, but it almost always is. This line here has an equation of y equal to -x plus 5. This side here is y equal to 0. This side here is x equal to 0. Oh, I forgot. I did something. Oh, man. There's something I did last. So after this, we'll go back to a problem from before just to show you something cool that I did that I think is worthwhile, not just cool. So with finding absolute max and mins, we have to find the critical points, the regular ones. We have to look at the corners, and then we also have to look at the extrema on each boundary, meaning we have 3 boundaries we're going to have to check out. Let's just find the regular critical points first. So regular critical points, take each of the partial derivatives, set them equal to 0. So the partial with respect to x is going to be y minus 1 equal to 0. That's easy enough. You get y equal to 1. And fy, the partial derivative is going to be x minus 2 equal to 0. So we're going to get x equal to 2. Well, that's easy peasy. We get a critical point of 2, 1. And importantly, that critical point is in the region, right? 2, 1 is right there. If it was 2, -1, we wouldn't have a critical point in the region, right? If that had been a plus x instead of a minus x, we wouldn't have a critical point inside our region. Okay, let's look at the borders. So let's look first at x equal to 0. Now sorry, y equal to 0. We look at y equal to 0. Our function now is going to be f of x comma 0 equal to 3 plus 0 minus x plus 0. So that's our function. Notice that it's linear. And when we take the partial derivative, what do we get? 0 minus 1. What that means is along that edge, the function is essentially always decreasing from left to right. So along this edge here, this corner is the highest corner, this corner is the lowest corner, and there can't be a relative max or min in between. It doesn't like do this or like this, right? It's just like down from left to right. Meaning we don't have any critical point on that boundary, and we still are just going to look at the corners. So no critical point there. Right? That doesn't equal 0. It equals -1. And the same thing's going to be true for the x equals 0 border. Look at x equal to 0, we're going to have f of 0 comma y equal to 3 plus 0 minus 0 minus 2y. And if we take the partial with respect to y, we're again going to get a non-zero constant. It's going to be -2. That doesn't equal 0, so we get no critical points.
Can you put the -1 then?
Sure, the same thing that the -2 means is that since that, so basically for the -1 along this border, so I'm going to try and do a bad drawing, not a bad drawing, but the best thing to do. So basically what's happening here is if we draw this in 3 dimensions, sure, we can try this. So so here's my x-axis, here's my y-axis, and my region looks kind of like this, right? And then what I'm saying poorly, well, if I plug in 0, 0, I get 3. What I'm saying is in the y direction, so this one here along x equals 0, my slope of my surface in that direction is -2, meaning if I move just to the right, I'm essentially just going down like that. And similarly, in the x direction, if I move from this point here, I move just in the x direction, I'm just going to go down like that. So that there isn't any sort of like hump or bottom out. It's just a straight going down from left to right or down from front back to front so that you don't get a critical point in the middle somewhere. However, if we look at the third border where y equals negative x plus 5, well, then we're going to have f of x comma negative x plus 5. And we're essentially just going to plug in negative x plus 5 for y and get 3 plus x times negative x plus 5 minus x minus 2 times negative x plus 5. Let's simplify that before we take the derivative. That's going to equal, let's see, 3 minus x squared plus 5x minus x plus 2x minus 10. Simplifying even further, that's going to be negative x squared, 5x plus 2x is 7x, and oh, minus another x, sorry, is 6x, apologies. And then 3 minus 10 is negative 7. And if you take the partial derivative of that, your fx is going to be negative 2x plus 6. Set that equal to 0, you're going to get x equal to 3. And if x is 3, y is going to be negative 3 plus 5, so y is going to equal positive 2. So right up here at the point 3 comma 2, there's another critical point. So what's happening there is along this boundary here, the curve might, I don't know if it's a max or a min, but the curve might be doing something like that. Where if I go 3 this way and 2 that way, right, it's kind of, it might be maxing out right there. So like my surface might look like this over that region. So that's the idea, is along this border, oh yeah, the function has a place where the derivative is 0, so we might have either a topping out or a bottoming out. So it's a candidate for being the absolute, either max or min. And I've run out of room, so I'm going to use paper. So now we're going to check all of our critical points as well as all of our corners. So we need to check 5 points. We need to check our corners 0, 0, 0, 5, and 5, 0, as well as our critical points 2 comma 1 and 3 comma 2. So we're going to take each of those, plug them into the original function, which I'll write down here so we don't lose it. 3 plus xy minus x minus 2y, and just see which one gives us the biggest y value, which one gives us, the biggest function value, and which one gives us the smallest function value. So f of 0, 0 is going to be 3 plus 0 minus 0 minus 0. F of 0 comma 5 is going to be 3 plus 0 minus 0 minus 10, which is negative 7. F of 5 comma 0 is going to be 3 plus 0 minus 5 minus 0, which is negative 2. F of 2 comma 1 is going to be 3 plus 2 times 1 is 2, minus 2, minus 2, which is 1. And finally, f of 3 comma 2 is going to be 3 plus 3 times 2 is 6, minus 3, minus 4. That's going to be 2. And then which one's the biggest? It looks like it is 3. Which one's the smallest? It looks like it is negative 7. So we have an absolute maximum at 0 comma 0, and absolute minimum at 0 comma 5. Kind of neat. I don't want you there. 1 second. I have one other thing I want to just mention. If I can find it. Yeah. So I don't know if you recall, but in the class where we talked about these absolute maxes and absolute minimums, we did talk about, so I'll just remind you briefly here. We previously talked about the function f of x comma y equal to x squared plus y squared plus x squared y plus 4 over the region. I think it was over the region where x was between -1 and 1 and y was between -1 and 1. And we did and you can look back in your notes or on my notes, and like we found a bunch of critical points. I think there was like 7 or 9 of them. And then we plugged them all into the function and we said which one was the biggest, which was the smallest. I think I actually made an error on that and said like one of them was the minimum when it wasn't. But I just want to point out, here's what this looks like. So here's the function. And actually, I'm gonna change this a little bit here. So if I just for a second here, I'll do this. I'll copy it. Yeah. Copy that. And then if I delete that, there's the entire surface. So clearly, none of these points that I've plotted on it are actually absolute maxima or minima, right? Because that function gets negatively large and positively large. So there's no actual absolute maximum. There are definitely some relative extrema, right? You can see down there, right? There's definitely a relative minimum at the origin, that whatever color that is down there, that green point down there, that's a relative minimum. There's probably some saddles over here or something. But that point up there, right? These are definitely not maxima or minima. But then if we add back in our boundary restriction, well, then the points that are the corners or the relative, the critical points then become candidates for absolute maxima or minima. Whoops, let's go back to the standard view there. There we go. So you can see, oh yeah, these 2 points up here are definitely absolute maxima. And this point in the middle down here, which now we see it's rotating, that's your absolute minimum. If you turn it upside down, it's the absolute maximum. And then we also had some candidates on the borders, right? Specifically, right, this blue, oh, not too close, James. Oh my God, sorry. It's kind of hard to control this sometimes. Let's go back to the standard there. Whoops, zoom in, zoom out. I don't know. I've killed it. There we go. Sorry, oh, I remember I did something weird with the viewing box. Anyway, hopefully you can kind of see, although I feel like it's kind of hard to see, that point right there, that purple point right there. I turn it on and off. It was one of those border points that might have been a maximum or a minimum. And it certainly is a minimum in that direction, but it's not an overall absolute minimum because there are other lower points on the entire surface in this region. So I think it's kind of neat to graph those things. Not super necessary, but just kind of cool to see. All right. That's all I've got as far as that goes. So let's talk about what's coming. So we're pretty much, this is kind of the end of this 3D graphing, maximum, minimum, average value, double integral stuff. Like after this, we're kind of moving on to something completely different, where we're going to be having to remember about some 2x2 matrix stuff that we did last quarter. So it's coming back, right? I promised you it was coming back. It's definitely coming back. So let's kind of build it up then. So moving along to new stuff. How much time do I have? I have 12 minutes. Okay, so I'm going to remind you of a couple things. You might not need to write this down. You might just want to watch for a second. So I'll remind you to recall something from last quarter. So recall from 17b that we had a differential equation that was kind of important. Specifically, we look at the differential equation dx dt equal to a times x. So what this says here is the rate of growth of whatever x is. We often think of like a population of people or animals, is a multiple of or proportional to the population size itself. And we learned how to solve a differential equation like this, right? So if we write this out, well, I can separate variables. Don't worry, there's not a whole lot of like solving differential equations in this class, just but we're kind of using this one specific differential equation to talk about the thing we're going to talk about. So we're going to separate variables. We're going to get 1 over x times dx equal to a times dt. We're going to integrate both sides. The integral of 1 over x is the natural log of x. I'm ignoring the absolute value here because we can. The integral of a dt, a is a constant, so we're just going to a times t plus c. We're going to solve for x. So we're going to say that e to the natural log of x is equal to e to the at plus c, which is e to the at times e to the c. And we're just going to call that a new constant, which we usually call c. So we have c e to the at. So our solution to this differential equation is x as a function of time is equal to some constant times e to the at. And then if you were to find, if you were to be given an initial condition, you could find the constant c. I will point out that if a is greater than 0, the population is growing, right? Because the rate of growth is a positive multiple of the population size. So if a is positive, x of t is growing. And if a is negative, x of t is shrinking. Population grows, population decreases. Okay. So, do I have enough time? Yeah. So we're gonna keep that in the back of our mind when we talk about how we're gonna solve this next sort of thing. So what we really want to be able to do, we're gonna skip ahead here for a second, is the following. So here's the actual kind of stuff we want to be able to solve. We're gonna let, x1 of t equal the population of predators. Think wolves. And x2 of t is equal to the population of prey. Think deer. So then dx1 dt is equal to the growth rate of the predator. And dx2 dt is equal to the growth rate of the deer, of the prey. And we would expect, so this will look better. We would expect that these populations are dependent on each other, right? More wolves, less deer, but then less deer mean less wolves, and then less wolves mean more deer. And it's kind of like a cycle going back and forth. There might be some sort of equilibrium and things like that. So let's look at this example. Let's say we have the following situation. We're given that dx1 dt is equal to negative x1 plus 2x2, and dx2 dt is equal to negative 3x1 plus 4x2. And some initial conditions, x1 of 0 is equal to 2, x2 of 0 is equal to 4. So again, if you're thinking about this is the rate of change of the predators, having more predators is going to be harmful because it's going to lead to less prey. Having more prey is going to be beneficial because there's more to feed on. I know that's a very kind of basic interpretation of this, right? Like I'm not getting into all the biology of it, but I'm just trying to make it make a little bit of sense. Okay, let's write this as a matrix equation. This is going to become the vector of derivatives dx1 dt, dx2 dt is equal to the coefficient matrix -1, 2, -3, 4 times x1, x2. Or as you might write this in a more compact notation, the derivative of the vector x is equal to the matrix A times the vector x. Hey, that looks kind of familiar. That looks a lot like the derivative of x is equal to A times x. And they look familiar for good reason. They have similar solutions. The problem here is that you can't really just say that the solution is a constant times e to the AT, because there's not a good interpretation of what e to a matrix would be. So this is where, to solve this, we need the eigenvalues and eigenvectors of the matrix X. So I want to leave you hanging here. Go back. So let's go and find them relatively quickly here. I know we only have a few minutes, but we'll do what we can. So here's okay. Let me get to the point actually instead of the solving. So the point is going to be that last quarter in 17b we talked about eigenvalues and eigenvectors, and the whole point of an eigenvalue eigenvector pair is that if lambda is an eigenvalue of the matrix A with associated eigenvector V, then that means that matrix A times the vector V is equal to constant lambda times the vector V. Multiplying the matrix by its eigenvector is equivalent to multiplying lambda by the eigenvector. Or in other words, A times the vector just gives you a multiple of that vector. But we're kind of looking for that to happen because we essentially want this thing to give you a multiple of itself. Or I should say the derivative to give it a multiple of itself. So when we're trying to solve this, we're kind of looking for that kind of thing. So what ends up happening here is that our solution here, our solution to dx dt equal to A times x is going to be the following. It's going to be kind of complicated, but it's essentially going to be our c e to the AT, except here's the matrix slash vector version of that. It's going to be, make sure I write it the right way here, the vector x1, x2, which is just the vector x, it's going to equal c1 e to the lambda 1t times v1. So I'll remind you that there's two eigenvalues and two eigenvectors for most of these 2x2 matrices, plus c2 e to the lambda 2t times v2. So essentially, c e to the constant times t times your thing, times your vector. So it's a similar-ish idea. It's not exactly the same, but you can kind of see, and we will see on Friday, that if you took the derivative of this, you would essentially just get c1 times e to the lambda 1t times lambda 1. You would get that multiple of itself coming back, just like, sorry, just like over here, right? The derivative of this x prime of t is just c e to the AT times a, or essentially it's x of t times a. So that when you take the derivative, you're just getting a multiple of the population already. The same thing is going to be true here. If we take the derivative of this, it's essentially going to end up being a multiple of the population. But this is how we deal with a more complicated system of differential equations as opposed to just a single differential equation. Sorry to not leave you with the solution to this, but we will definitely do it on Friday, and hopefully this will prime you to see what he's going to talk in class before he talks about it.